Hi everyone. So I know it's not the evening, but last night didn't work because I couldn't get my iPad to share, and also the days before that my pain was too bad, and today I got my iPad to work and also my pain is not too bad. So I thought I may as well just jump on and do the variable acceleration bit with you. And then for those of you who aren't able to watch it now, you can watch the recording. So at least then it exists. Okay, so variable acceleration questions. We're focusing on the AS because if you can confidently do the AS questions, then basically you're fine on the second year questions. There's a slight extension, which is that in the second year there's 2 dimensions instead of 1, but really that is not a big deal. This is a really good foundation for building that second year variable acceleration, so that's why it's worth us spending time on it. So how do we identify the topic? Really simple. The question has got on it either S equals and then a function with some t's in it. How did I see like that? Apologies. Okay, either it has S equals, or it has V equals, or it has A equals, and these will have T's in. And that's it. If you spot that, then it's a variable acceleration question. So we're going to go through the questions that I've picked out and see how we can highlight that it's a variable acceleration question. And then I want you to look out for 3 things. One of them is instantaneously at rest. One of them is changes direction, and then another one is the distance between 2 known times. Okay, distance between 2 known times. Instantaneously at rest or changes direction, distance between 2 times. Okay, oh my goodness, how do I make this so that I don't have to keep, one day I will become competent with modern technology, and apparently that day is not today. Video capture. Okay. There is a... Ooh. If I was recording easy, I could just press pause while I did this, but I'm doing them live deliberately so that you can ask questions, and also because otherwise I'll never do it. So how do I make this smaller? Aha! Ta-da! Now, I think you see what I see. Fingers crossed. Okay, so question number 1. How do we know that it is a variable acceleration question? Because it's got V equals with t's in it. We're looking for instantaneously at rest and the distance, not displacement, the distance from one time to another, or change of sign. Okay, this is how we know it's variable acceleration. Here we have instantaneous rest. There's nowhere... Oh yeah, it says distance as well. The distance from when it first comes to instantaneous rest. So that is the distance at a particular time, not the distance between 2 times. So that's not what we're looking for. But we have seen instantaneously at rest there. Okay, how do we know it's variable acceleration? Because it's got a function like that. Do we have instantaneously at rest? No. Do we have the distance between 2 known times? Nope. Okay, how do we know it's variable acceleration? Because we've got an equation here. Do we see instantaneously at rest? No. Do we see distance between 2 points? No. Here's how we know it's variable acceleration. Here's instantaneously at rest. And here's the distance between 2 known times. This is going to be the classic question that you're going to see. This is how we know it's variable acceleration. This is the distance from t is 0 to t is 10, and there's no instantaneously at rest. This is how we know it's variable acceleration. Here's instantaneously at rest. Here's the distance between two known points. Here's how we know it's variable acceleration. We don't have instantaneous rest or changes direction, and we're not asked to find a distance. This is how we know it's variable acceleration. We don't have instantaneously at rest, but we do have changes its direction of motion. And we are finding a distance between two known times. One of the times is the beginning, time 0, and the other one is this time here, where it changes its direction of motion. This is how we know it's variable acceleration. Here's instantaneously at rest, and here is the distance between two known times. Here's how we know it's variable acceleration. Doesn't mention instantaneously at rest or changes direction, doesn't ask us for a distance. Okay, well, 7 to go. This is how we know it's variable acceleration. Here we've got instantaneously at rest. Actually, it's mentioned twice. And then we've got the distance between two known times. This is how we know it's variable acceleration. Here we've got instantaneously at rest, and here we've got the distance between two known times. This is how we know it's variable acceleration. And we don't have instantaneously at rest, but we do have the distance between two known times. This is how we know it's variable acceleration. We don't have, yes we do, instantaneously at rest. And they're not asking for the distance between two known times, but they're telling us the distance between two known times. So it's kind of relevant, but we're not being asked for it, we're being given it as a fact. Okay, this is how we know it's variable acceleration. And we don't have instantaneously at rest anywhere, but we do have the distance between two known times, or two given times. This is how we know it's variable acceleration. No mention of instantaneously at rest, no mention of distance. This is how we know it's variable acceleration. No mention of instantaneous rest, no mention of distance. I think that's the last one, yes. Okay, so why are those things relevant? Well, excuse me. Instantaneously at rest is a piece of information that we need to translate. When it says instantaneously at rest, what we're going to change that to, and the thing that we're going to actually use, is the velocity is 0. So instantaneously at rest, velocity is 0, and actually change direction is the same. If something changes direction, then on your VT graph it's going from up here, where we're going forwards, to down here, where we're going backwards, or the other way around. Maybe it's going from backwards to forwards. Either way, that moment there, when V is 0, that's when we transition from one direction to the other direction. So both those things are going to be V is 0, so it's going to be just a translation into something we can use in maths. When you see distance from time A to time B, this is going to mean that we're going to be doing integration. But here's the important thing, we're going to be doing definite integration. We're going to be integrating the velocity, because as you know from VT graphs, the area under is the distance. So to find the distance from this time to this time, we're going to be integrating the velocity. Unless they already gave us the function for distance or displacement. But usually we've got the velocity at this point, and we're going to integrate the velocity. And here's the important thing. We're going to integrate it from this t to this t. So we have definite integration. So even though we are going to do integration, we're not introducing a plus c, because we've got definite integration, because we're going from this time to this time. So there isn't going to be a plus c. And that's going to be relevant for the style of questions that come up. So let's just have a little flick through and see what that tells us. So here, find the distance of the bird from the nest when the bird first comes to instantaneous rest. So instantaneous rest, v is 0. So we're going to solve v is 0 to get a time. And that time is the time that we want to start our measuring of the distance. Find the distance of the bird from the nest when it's at this particular time. So we're going to find that particular time by solving v equals 0. So it's a sub-problem. Okay, instantaneous rest, v is 0. Find the times when v is 0. So we're going to be solving v is 0, and then that will be the end. We'll solve v is 0 and we'll have the times when p is instantaneously at rest. Okay, now find the total distance travelled between 0 and 2. 0 to 2, and then here goes the velocity, dt. Now, have a look at this one. We're not actually given the velocity, we're given the displacement. So we don't need to actually integrate the velocity to get the displacement because we already have the displacement. Does it matter that there isn't a plus c? No, because if there was a plus c, they would tell us and it would have already been given to us. And also because we're going a definite integral, so we're subbing in t as 2 and then subtracting and then subbing in t as 0. So even though normally I would have to do this, because I've been given x equals, I've been given the integrated version of the velocity. I have it already. And I know I'm going to go from 0 to 2. And then I will have solved that one. Okay, distance. Now they are giving us the velocity here, so now I am going to have to actually integrate. So I'm going to integrate the velocity from t is 0 to t is 10. Instantaneous rest, v is 0. Find the magnitude of the acceleration when v is 0. So I need to know what time this happens, v is 0. So we're going to solve v is 0. That's going to give us a time, and then we're going to use that time to find the acceleration. Changes its direction of motion is also v is 0. Find the distance at the time when v is 0. Okay, so again we need to find when v is 0. So we'll solve v equals 0, we'll get t equals something, and then we'll use that to find the distance that they want. Instantaneously at rest, v is 0. State the values of t for which v is 0. So we're just going to solve v is 0. Instantaneous rest, v is 0. Now, find the times when p is instantaneously at rest. That means solving v is 0. But look, it's got an unknown in, a k. V equals something, it's got k's in. So how can I solve an equation if I've got some missing bit in it? That's going to become a common theme in these questions, this missing information. How do I find that piece of missing information so that I can answer your question and solve your problem? So that I'm going to come back to, but basically we just need to solve v equals 0 and get the time. Instantaneously at rest, v is 0. Find the acceleration at the times when v is 0. So again, we're going to solve v is 0. That's going to give us some t's. Then we're going to take those t's and use that to solve the problem. Okay, distance. So we're going to be integrating the velocity, and we're going to go from 2 to 10. They gave us velocity in this one, so I'm going to have to integrate the velocity from 2 to 10. Instantaneously at rest, v is 0. Determine the time when p is instantaneously at rest. Okay, so basically we need to solve v is 0. That's our ultimate aim. But v has got unknowns in it. V has got a k. We've already seen this once, we're going to see it many times. So they have to give us a piece of information so that we can find the k, so that we can know v, so that we can solve v is 0. It's going to be a common theme. Integral. They give us velocity. We're going to have to integrate the velocity from 0 to t. And we've already found t in the previous part of the question, so we would know what it actually was. Okay. Next theme to point out with these. So we've talked about the most common things to look for that come up in most of the questions. One of them is knowing that instantaneously at rest and change direction means v is 0. And the other one is that if they want a distance between 2 points, then it's an integral. We're going to look back through now and just check those integrals for something really important that is a common mistake that students make. So I'm just going to look where those integrals are. That one, we didn't actually need to integrate because they told us the function. I'll come back to that one. Okay, this one. Now, what's important here is they're asking for distance, not displacement. Now, if I integrate that and do the limits, I will get displacement, and it might not be distance. Why? Because when we integrate curves that do that, then we get some positive and some negative that cancel out, and that is the graph, the VT graph, showing the particle going backwards and forwards. If I go back forwards a load and then backwards a bit, my distance travelled is not the same as the displacement, which is how far do I end up from where I started. All of these questions, they are asking you for distance, not displacement. If it said displacement, then we could just go ahead and integrate and put the limits in, but it never does. It says distance. So I need to know what that VT graph looks like so that I can tell whether or not I need to break my integral up into bits. So sadly for everyone, this is where a bit of graph sketching does come in. So let's look at the velocity. It is a negative cubic, the velocity. So it's going like that. It's got a double root at t is 0, because it's got a common factor of t squared. If you look at that v, I can pull out a t squared. That means it's got a double root at 0. So either that's where the double root is, or the maximum point is where the double root is. I'll think about some more things that could tell me what was going on. I guess I could differentiate and see whether I had a turning point at the origin, and then that would tell me whether or not it's looking like that or looking the way that I drew it before. So I think I'd probably have to do that to think about what this graph looks like. Isn't this all a total pain when all you want to do is integrate and stick the limits in? But that might not get you the marks because you'd be finding displacement, not distance. Okay, here is the gradient function. So if I differentiate and sub in t is 0, then I get, so this is my original function is v. dv by dt is 0 at t is 0. I already knew that. It was going to be the maximum, the double root. But is the double root the minimum or is the double root the maximum? Okay, so now I'm going to differentiate again. d squared v by dt squared. So that's the first derivative of a, because a is the first derivative of v. So that's going to be 0.96 minus 1.42, I think, t. So I'm going to sub in t as 0. My second derivative comes out positive, so it's a minimum point. At t is 0, I have a minimum point. Okay, now I've got an idea of what this graph looks like. Now, is it going to go, where am I going from? 0 to 10. Is that going to tip past that point where it goes down there? Because if so, I need to split this integral up. So now I need to know, what is this point? Okay, when is v 0? So I've got 0.48 t squared minus 0.024 t cubed. I'll pull out the t squared. 0.48 minus 0.024 t. Okay, when is that 0? When t is 0, I already knew that one. And when t is 0.48 divided by 0.024. Oh my goodness, I have no idea what that number is. Go to pee. That number could be anything. 0.48 divided by 0.024. 20. It's 20. Yay! That number is 20. Which means when I integrate from 0 to 10, everything is absolutely fine. It's all above, it's all forward. That means that that will get us the right answer. But wasn't that a faff? Let's see how many times it gets us the right answer and how many times we have to adjust it. Distance travelled, so we think we're going to do the integral from 0 to 3 of 12 plus 4t minus t squared dt, but that would get us the displacement, not the distance. So I'm going to have to draw the velocity, draw that vt graph, and see whether or not I need to split it into two bits. V is a negative quadratic. It's minus t squared plus 4t plus 12. Let's see if I can factorise that. Minus t squared minus 4t minus 12 minus t minus 6t plus 2. So I think we're going through 6 and minus 2, and it's a negative quadratic, like that. And this is going to be the important bit, 6. T doesn't exist for negative t, so I can get rid of those bits. Just like that. Okay, what was the point of that? Because I want to know whether or not I need to split my integral, which goes from 0 to 3, up into 2 bits. And I don't. Here's 3. I can integrate from 0 to 3, absolutely fine, and I will get the distance. It will be the displacement as well, because there's no change of direction. V doesn't equal 0 on that interval, so everything is fine. Okay, this one, we're doing the distance, but in order to find the time that we're going at the top of the limit, because it's from time 0 up to time whenever it is that v is 0, I would need to solve v as 0, but that's going to be the same as me sketching it anyway, so I'm going to do the same problem. Basically, I really need to know what this vt graph looks like. So it's a negative quadratic, and it goes through minus 2 and 3.5. We don't need any of the bits where t is negative, because time can't be negative. And we're going to be integrating, and we're integrating from the beginning to the time when it changes direction, which is when v is 0, which is at 3.5. So my integral is going to be all of this. It's all positive. I can go straight away from 0 to 3.5, integrate the velocity, and I will get the displacement, which equals the distance, because there's no changing of direction on that interval. Here's the velocity. Am I safe to do this in one go or not? Let's look at the VT graph. So it's a negative quadratic. It's going through 3 and minus a half. We don't have any negative t, so we don't need to worry about that. This one is 3. Oh, this is the first time they've done it. The top limit is 4. So if you'd done all those other past papers and never thought about this, you would have been like, yep, every time it's the same. You can integrate from there to there, and you integrate the velocity and you put the limits in, you get the distance. No, you get the displacement. It's just they haven't tried to trick you before. So this is really, really important, that every time you look for that trick, even though it does mean sketching the velocity graph to have an idea what it looks like. So in this one, that 4 comes after the point where it changes direction. It changes direction at 3. Forward, 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 instantaneously at rest, backwards, backwards. So they were kind of giving you a hint in part B that there was a change of direction, because they said, when is it instantaneously at rest? It doesn't have to change direction. It could go forwards, 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 slow, 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 stop, speed up, keep going forwards. But in this one, it doesn't. It changes direction. So you need to integrate from 0 to 3. Then you need to integrate from 3 to 4. The 3 to 4 bit will come out negative. You'll ignore that minus sign and add it to the bit you got when you integrated from 0 to 3, and that will be the distance. Okay. Oh, same thing. Now we're integrating from 0 to 6. So let's have a look at this. It's a negative quadratic. It's got a k in it that I don't know, but I will know it after I've done part B. So in part B, I am going to I'm pretty sure in part B I'm accidentally going to find out what t is, because it says the particle is instantaneously at rest when t is 6. So they're telling us that if t is 6, v is 0. So if I quickly just sub those in, v is 0, t is 6. Okay, 60 minus 36 is 24, k is 24. Okay, so now that information gave me my k, and now I don't have an unknown anymore because this guy is 24. Right, so I've got a negative quadratic, and the negative quadratic is minus t squared plus 10t plus minus 24. Let's see if I can factorise that. It's minus t squared minus 10t plus 24. 24, 12 and 2 minus 12 plus 2. No, that doesn't work. 6 and 4 minus 6 minus 4. That works. So it's a negative quadratic going through 6 and 4. Okay. Where do I want to find the distance? 0 to 6. Okay, nice try, examiner, but I can see that I need to split this up into 2 bits. I need to do, first of all, the 0 to 4. That bit's going to come out negative, but I'm going to ignore the minus sign. Then I'm going to do another integral from 4 to 6 to get this area, which is the forward bit. So this particle starts travelling backwards. So it's going in that direction at the beginning. And it goes in that direction for a while, but it slows down, and then at time 4 it stops and turns, and now it starts going forward, and it goes forward, 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 and then at time 6 it's going to stop and turn around again. Not that we're interested in what happens after time 6. Okay, total distance travelled between 0 and 4. Okay, we now have the same situation as that one at the beginning, where they've actually given us the distance function. They're not giving us the velocity, they've given us the distance function. So if I plug in 4 at the top and 0 at the bottom as my limits, then I will get the distance. And you can even see it here, look, s is the distance, not the displacement. So that's great, s is the distance. Everything is telling me it's okay, you don't need to worry. You don't need to differentiate it and then draw the VT graph. You can just use it straight away. Okay, now this one, 2 to 10, we can see that there's not going to be a problem because 2 is here and 10 is there, and we're going to find that area by integrating the velocity from 2 to 5, and then this is a rectangle. So because they gave me the VT graph, I don't have to worry about the VT graph going negative, which means the particle changed direction, which means I have to be careful with distance because they gave it to me. So I can literally just integrate, but I'm not going to be integrating from 2 to 10 because the equation only goes to t is 5. So I'm going to be integrating from 2 to 5 and then working out the area of that rectangle and sticking that on, and that will give me the distance. Okay. This one, they're telling me an area. Why are they telling me an area? They're saying that from t is 1 to t is capital T, which is just a random point, I think, that area is 297 metres. find the time when P is instantaneously at rest, so we're going to try to solve V is 0. Now we do have V, look, so why can't we just put V equal to 0? Because there's a piece of information in there missing, it's got a K in it. We don't know K. So in order to solve V equals 0, first we have to find K. This is going to be a common theme. Did we do this one? We want the distance travelled from 0 to T, the maximum velocity. Okay, so this one we are going to have to split it, aren't we? They've given me the graph, the VT graph. I can see that this particle starts off going backwards, gets faster and faster and faster and faster, and then starts slowing down and then stops and then changes direction. Here it's instantaneously at rest, changes direction, starts going forward again. So if I want to know the distance, then I need to integrate from the T is 0 to that point there, and then from that point there to capital T. The first one will come out negative, we'll ignore the minus sign and we'll add them together. So how am I going to find that question mark? Well, they've given me the equation of V. This is the equation. So they sketched it for me, but I can see the equation, so I can see that it's a negative cubic. Dun, dun, dun. It's factorised for me, so I can see the roots are 0 and 3 and 8. So this must be 3, and then down there somewhere will be 8. And now I can go ahead and do my integration. Okay, so summary so far. You know how to identify the topic. You know to look for instantaneously at rest and changes direction, and to just cross those out and change them to V equals 0. You know that distance from a particular time to a particular time is a very, very common question, and that you are going to be integrating the velocity function, or with definite integral from time A to time B, or maybe they already gave you the distance function, in which case you will be just doing the limits bit where you sub in the top and sub in the bottom and subtract. But you also know the examiner trick. The examiner trick is to have a particle which changes direction, meaning that the velocity graph goes through T V equals 0 and goes from below to above or above to below. And then if that is happening and you integrate from there to there and you don't take into account that change in direction, you won't find the distance, you'll find the displacement. And because it's an examiner trick that doesn't always come up, you could be lulled into a false sense of security. So the message is, if you're integrating, look at the VT graph. The VT graph will tell you what to do. Now the last thing that I'm going to mention with these questions is the unknowns and linking information with unknowns. Now there's two ways that the examiners slip these unknowns into the question. One of them is it's in the function. Unknown in function. So they might give you S equals or V equals or A equals and something in there you don't know. Or they give you a function where you do know everything, but then you have to integrate it. And when you integrate it, you get a plus C. And you don't know the plus C. So those are the two ways these can be introduced. In order to allow you to find that unknown, they have to give you a piece of information. And this is true of every modelling question that you see. So a modelling question is one where they give you an equation, a function, but it's got bits in that you don't know, maybe an A and a B or a K or something that you don't know. They're then going to give you pieces of information, and the number of pieces of information will match the number of things that you don't know. By subbing that information in, you get an equation. By subbing the next piece of information in, you get an equation. And then by using those equations, and possibly simultaneous equations, that's how you find your unknowns. So one unknown, one piece of information. So let's have a quick look through for how many times they do that, either by giving you the unknowns or the unknowns being introduced with a plus C. So in this one, there's no unknowns in the function. They give us V, so if we have to integrate, there will be a plus C. They say find the time when the particle passes through the origin, so we need this, so we do need to integrate. So we are going to introduce, as we do this, an unknown. So then where is the piece of information that tells us the unknown? Okay, let's see. Initially at rest. No, that's not our piece of information because we already know that. Initially at rest means when t is 0, v is 0, but I can already see that by subbing in t is 0. Might have to actually do this to see what happens. So find the time when the particle passes through the origin. Okay, so let's have a look at the VT graph. That's going to help. It is a negative cubic. It's got a double root at 0. So I think it's doing something like this. So the particle is going forwards, 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 and then slowing down. No, it's getting to a maximum speed, forwards, forwards, forwards. Now it's starting to slow down, still going forwards, 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 forwards. And then it's going to stop, and it's going to change direction, and it's going to turn around and come back towards me, getting faster and faster and faster. So when it next passes me, say I'm the origin, when it next passes me, is going to be when its displacement is 0. The moment when it passes me again is the moment when all its forwardness has been cancelled by all its backwardness. So those areas are exactly the same. That is the time that they're looking for. So here's what we would need to do. We would need to say, I'm looking for a time. I don't know what that time is, but I know that the integral from 0 to that time of this velocity function, 6t squared minus 12t cubed, I know that that is 0. Because that's what I'm trying to find. I'm trying to find the time when the particle is exactly where it started. So the displacement is 0. So we would solve that, we would integrate, we would sub in the limits, it would get us an equation, and then we could solve for t. So did we need any unknowns? No, because yes, I did integrate, but I had a definite integral. It was going from time 0 to the time I wanted. So even though I didn't know the time I wanted was part of the definite integral, but it's still a definite integral, which means I don't have to worry about the plus c. Has this got any unknowns? No. No unknowns in there. No unknowns. I'm just looking for unknowns in the function at the moment. Nope. That function we know everything. That function we know everything. Yep, we know everything. Yep, still know everything. Yep. Yep. So most of the time, these aren't modelling questions. Aha. Here's our first one. It's got a k in it. Remember that one from a minute ago? How did I find k? I needed the information. Here was the information. When t is 6, v is 0, that is what connected me up and got me that value of k. Nope, this one's we know everything. Oh, this one we don't know 3 things. We don't know P, we don't know Q, we don't know R. So there must be hidden in here 3 pieces of information. Okay, I can see one of them really easily here. When T is 0, V is 18. Here's another one that's really easy. When T is 5, V is 9. But that's only 2 pieces of information. I need 3 pieces of information to get 3 unknowns. Here's the third bit. The acceleration is 0 at t is 5. So that third piece of information says when t is 5, a is 0, no acceleration. So I'd need to differentiate v to get a, and then I can sub in t is 5 and a is 0. Now I've got 3 equations, one coming from each piece of information, subbed into its relevant equation, and then I can do simultaneous equations and I'll find the 3 unknowns. This one had a k in it. The velocity was minus 3t squared plus 24t plus k. So where's the information? The information is here. The distance between there and there is that, which means I can integrate. Oh, hang on, because I don't know t either. Let's work this one through. If I integrate from 1 to t, and I integrate the velocity, I know that this will come out to be 297. So I can integrate, but there's a k in there, so there will be a k in here, which means at the moment, if I complete that, I put in the t and then I put in the 1. I get an equation, but there's two things I don't know in it. I don't know capital T and I don't know k. So what am I actually trying to find? Let's work this one through more slowly. A particle P moves in a straight line. The velocity is v. We know the velocity apart from we don't know what k is. This is k. It's the velocity at time 0. The diagram shows the velocity. Oh, didn't read the question properly. The maximum velocity is achieved at time t. The maximum velocity. T is not random. T is not just like, oh, I don't know anything about t. T is this very, very special point here. At t, the acceleration is 0. Now luckily when I differentiate the velocity to get the acceleration, that problem k disappears, which means I do know the actual equation for acceleration. So I can sub in a equals 0 and then find out what capital T is. Hooray! Now that I know what capital T is, now I can solve the problem. Well, no, sorry. Now I can't solve the problem yet, because even though I found out what T is, I still don't know what K is, but that's what that information there now does, because now I only have one unknown. I know T, which means that inside here, yeah, there is this hidden K, it will be in there, but there will only be one unknown, which will be the K, and I can solve that equation and find K. And then after all of that, finding what capital T is, finding what K is, now I know what V is, and now I can solve the actual problem. Solve V is 0, which is super duper easy. Okay, this one did not have any unknowns in. This one didn't have any unknowns in. This one has 3 unknowns again. A and B and C. So where's the information? The velocity at point 0, so this is the initial velocity, they're saying is the same as it was in part A. That's piece of information 1. The acceleration at the origin, so that's the acceleration at time 0, is the same as it was up here. It's 2 pieces of information. Q, this particle that we're looking at, reaches the point A when t is 6. Now we know how far A is away because we already found that out here. A is 18 away. So that piece of information is that when t is 6, the displacement is 18. And the other information is that when t is 0, A is this, and when t is 0, V is this. So those 3 pieces of information have to be subbed into the 3 relevant equations, and then you will get 3 equations, each of which have got an A and a B and a C. And then you'll use simultaneous equations to find the A and the B and the C. Pure modelling question. Then it says what's the velocity at the point. So now we know the velocity equation without any unknowns in, then we can find the velocity at that particular point. And that's the end. So, in summary, these questions are easy to identify. They commonly can have 2 things in them: instantaneously at rest or changes direction, which is V is 0, and distance, which involves integrating, but there's a common examiner trick to look out for. One of the big things that you're going to be doing in these questions is finding unknown values. Those unknown values, each of them comes from using a piece of information. So you're going to be looking around the question and saying, where is a piece of information? Then you're going to sub that piece of information into the relevant equation, and that is what is going to help you find your missing things, and then you'll be able to answer the actual question that they're actually asking you. So it's much harder than it seems. It's not just, oh, you differentiate to go down and you integrate to go up. That's the easy bit. Then it's understanding the question, understanding what you need to do. So I hope this outline has helped a bit with that. I will separately go through the actual questions doing them, but I wanted you first to see how common the themes are that come up, so that you can start to look for those themes when you're coming across a variable acceleration question. See you tonight, hopefully, for some second year stuff.